ask you. Appreciate it. All right. So this has been a great show for us. I think a lot of fantastic advancements in hardware and software in terms of user experience. But today we'll focus a little bit on a piece that is more hardware related on the impact of the battery on how consumers experience the AR, VR world. So typically, when we look at consumer experience on, take gaming for example, the usability, people look for longer battery life. You want to use your glasses for as long as possible before you need to recharge. However, given the advancements in battery technology that need to happen, whether you talk about materials, talk about chemistry, that takes a long time to do. The other piece of the puzzle then comes, how quickly can you recharge the battery? Do you really need to wait for an hour, 75 minutes, 90 minutes to charge? Or can you do that in 10 to 15 minutes? And that's really what we're going to talk about a little bit today in terms of advancements in charging technologies.
Yeah, so when you're charging a battery, I mean, inherently you are going to be causing battery damage. This is something that we've all seen day to day with our electronic devices, with our cell phones. You charge it up after, maybe a year and a half, 2 years, your usable capacity and battery life is significantly reduced at that point. And that's typically accelerated or exaggerated if you're using like a fast charger. Certain devices have this capability of getting you about half charge in maybe 15 minutes, but that's kind of a sliding scale on a give and take. So if you have a little bit faster of a charge, then you're actually doing more damage. There are some advancements that our company is looking into, which is really revolutionizing and taking a ground up approach to this charging algorithm and how it's delivered to a battery. This actually will minimize the damage to the cell. And then if you actually are doing less damage to these batteries, it actually ends up giving you a safer product. You get more performance, you get more battery life longer into the life of the device. And it also kind of prevents some of the problematic safety concerns that can arise with an older device as well. So talking a little bit about like the charging evolution, these algorithms have started out very simplistically with a constant current or constant voltage type approach. Those have evolved into something called CCCV, which this is kind of your bread and butter battery charger that you know today. There's some other variants that have come along throughout the years, which are known as DC variants, where they'll do step charging, burst charging at very early on. There's also the variations where they're doing AC stimuli to do certain functions within the battery's electrochemistry to help create a more advantageous charge scenario for that cell. And then this next generation charging that we're discussing today is really just taking this truly kind of fundamental electrochemical ground up approach, which really tries to create a uniform current density within the battery themselves. And when you do that, you really enable both of the performance gains that I mentioned of fast charge and extended cycle life of that battery. This really prevents things like hotspots from forming inside the battery, suppression of dendrites and better SEI layer uniformity, which are kind of like the main electrochemical elements within the battery.
So why is that important? So when you look at batteries and you charge and you look at the damage or the degradation mechanisms in batteries that come up first, it's primarily driven by the whole concept of non-uniform charge or current density that as the ions flow from the cathode to the anode in a battery. So this causes things like copper dissolution or SEI formation and buildup. You have hot spots that end up giving where lithium ions can deposit. You have things called dendrites, which are growth patterns that happen on your cell, on your electrodes. And that's essentially what causes, you hear about battery fires and things of that nature. That's what happens. You have dendrites, you pierce through the separator, and sometimes you go from the anode to the cathode. So that's what creates arcs, that's what creates fires. And that's really to what Billy was talking about. That's what constrains or slows down your charging that you can achieve. You have to slow down your charging, so slow down the current, slow down the energy that you're pumping into the cell to prevent these damage mechanisms from taking effect. So what that essentially means, to put it in a simple picture, when you look on the left-hand side, that's what conventional charging is. You have these ions coming in at random, flowing in, and when you have an anode surface, you do have some roughness on the surface of the anodes, micron level roughness. But when you have those roughness, you have peaks and valleys. And if these ions come in a random fashion, then what essentially happens is they're attracted to the peaks, sort of the tops of the, on the anode of the roughness. And as you have deposition happening there, and that's where your voltage hotspots are, so you get more deposition, and that's what causes your dendrites to happen. On the right-hand side, this is really the new generation of charging where you're not looking at the chemistry of the battery necessarily, but also looking at electrodynamics, not just electrochemistry. And the meaning of that, what you're trying to do is to get charge in a uniform fashion across the surface of your electrode. And that essentially what that means is you don't get these hotspots, you don't get these growths, and when you have these growths, you have more voltage. That's where you get your electrolyte decomposition happening, so you prevent all of that with the new charging techniques and methodologies that are coming about. So you do have better ion intercalation, so less damage. What that means is you can pump in more energy without fear of something going wrong. And for us, what that essentially means when you talk about more performance, it's essentially faster speeds, okay, without sacrificing safety, without sacrificing the life of the battery. You pump in more current. Or you could get a much longer cycle life. You don't have to change batteries out that often. You don't lose capacity of the battery over life. And that allows you to use your battery with the same performance for much longer. And especially for devices where you can't change batteries out, it means the device lasts longer for you. The other big advantage is you can do cold temperature or harsh temperature charging. Typically, lithium-ion batteries don't charge below 0 degrees C. And if you're trying to do something outdoor, that could be a problem. And so again, some of these new charging techniques allow you to be able to charge up to minus 20 or even minus 30 C. And last but not least, you're preventing dendrites from coming, you're preventing damage to the anodes and the anode, you're preventing damage to the cell. That means it's better product safety. And as we all know, lithium-ion batteries, safety is a big concern. And this allows product owners to be able to push the consumer experience to new levels without compromising on the life of the battery and the safety of the battery.
So I want to dive in on some zoomed in images here. So we see a fresh anode under extreme magnification here on the left-hand side. You can kind of see that porosity and that peaks and valleys structure that VC was referring to. And typically over the course of a battery charge, you can actually see this starts to look more like a, kind of like filled in, almost like sand on the desert approach, where you start to get this plating effect, where this is really just the breakdown of the internal electrochemistry, and this lithium is not free flowing anymore within the cell itself. It is actually permanently affixed to the anode. This is the major contributor to why batteries degrade over time. And the research that we're doing at Iontra is really looking at how can we minimize this effect. And you can see the middle graphic has 158 charge cycles on it. The graphic on the right has 500 charge cycles, and we only saw capacity degradation to 80% after that. And you can see it's in a much healthier state, much more like the left-hand side first image. We've also worked with numerous third-party validation labs and universities as well to help confirm these results with University of Michigan, NREL, Novonix, and UL. So, VC was also mentioning a fair amount about like these charge time advantages. And you can see, this pretty clearly of this benefits of this next generation charging. So the blue line on the left shows the charge time over each cycle that we've charged and discharged this battery at. And the yellow line represents our control case, where this is more of a conventional type of charge that you'd find implemented in a cell phone. You can see as you get out to cycle 100, your charge time is actually increased from 40 minutes to 80 minutes. So it's doubled in that scenario, and our charge time remains constant at 25 minutes. And the graph on the right is really, the telling piece here, because that's showing that we are maintaining the same amount of discharge energy retention over that cycle life as the control, while still charging much, much faster.
So the only other thing I'll add, Billy, to what you're saying is quite simply, I think this is how normal batteries behave. Over life, they degrade and the performance gets worse and worse and worse. So when you don't have damage, then you have a consistent performance. So it's not like your AR/VR glasses charge in 40 minutes today, and 6 months from now, it's going to take an hour. So you don't see the kind of loss of performance with some of these electrodynamic-based, charge density-based approaches to charging that are now coming into play.
Yeah, so what that means for the product integration side of things, right? I guess really talking back to the user experience of one of these products, maybe a AR/VR headset, it lasts 2 hours on a charge, but takes 90 minutes to recharge. That is a pretty significant amount of downtime if you're using this day in, day out, or it's part of your job. This is something that is going to be very impactful, and you're going to basically require a larger fleet of these devices to be able to maintain, that full amount of uptime and usage that is required for whatever the application or use case may be. So reducing this charge time is paramount to being able to realize those benefits. And we've also had to really focus in on the integration of this technology, because if it's not scalable, if it's something that's going to be very challenging to design into a product, it's of course going to be not very compelling for manufacturers of these devices and designers to be able to kind of take what it is that we are able to offer in the performance and actually realize it in the end product. So we have been able to evaluate your typical battery charging implementation and actually leveraging a lot of the same power supply topologies and componentry, pull off this means of advanced charging. And these product and system architectures can vary. You can see them on the left-hand side. We've got the device that has the charger and power input all enclosed. This is very akin to something like a cell phone. Then there's other devices where there's actually a distinct charging dock and device separated. And I kind of showed a line where those major system components live within those type of architectures. But we have demonstrated that we can actually realize this amount of charge performance and effective design with all of these different variations from product to product. And within that, there's also different power inputs, USB-C, barrel jacks, onboard AC to DC conversion, and that does not pose any major issues with our implementation. And lastly, the core componentry that exists within these devices, there are some modifications that need to be made, but there are a lot of overlap as well with the typical implementations that designers will use.
And that's one of the challenges, I think, when these new technologies people look at is how much change do you cause in your ecosystem? How much change or trouble do you cause the hardware providers, right? And for something to succeed and be adopted, there's a cost element to it and there's a complexity element to it. And the beautiful thing is some of these next generation new charging methodologies using electrodynamics do fit into current topologies, as Billy said. So that really helps in the context of somebody wanting to go in and implement this, on how quickly you can implement and how expensive it gets.
Yeah, and to kind of further drive that point home, we have designed a reference board. So this is a PCBA assembly, something you would deliver to an engineering team. And it's actually 100-watt USB-C PD input, so something very commonly found in modern electronic devices, and especially with the EU mandates for transitioning a lot of power supplies and charging inputs to USB-C. This is only going to be more and more prevalent in the future. This particular device and eval system can charge a 3-amp-hour battery, which is something that you'd pretty typically find in a cell phone or the AR/VR headset. We can charge from 0% to 100% SOC in 15 minutes, where a lot of times manufacturers are advertising that they can do that in only to like 50% SoC in 15 minutes. So this is quite an advancement in that rate of charge for this particular cell.
And don't be scared about the size. This is not what will go into a AR/VR device. This is more in terms of trying to give customers the ability to test the limits of the technology. There's a very small portion of the circuitry that actually needs to go on a product. And we are kind of, these kinds of technologies, electrodynamics-based charging technologies are currently being evaluated from cell phones to AR/VR devices to many hearables and wearables and a lot of very space-constrained applications. Yeah, and that's really what we wanted to cover today to show where from a user experience perspective, where really the market's going, where the technology is going, and how it hopefully will play a role along with the hardware and software in making AR/VR the momentum, continue to accelerate the momentum of these technologies in daily use. So, thanks.
Thank you.
Thank you so much, VC and Billy. I have so many questions, like myself. To be really honest, I think that it's amazing what you're creating, what you're talking about, actually. And it happens that, for example, what happens with the electric cars batteries that have to go into a 100 kilowatt thing for fast charging, how is that going to affect what you're building? Does it affect that as well? Because that's another major issue, right? But on a larger scale, you might say. And on the other hand, does the system that you've created to, optimize the charging process, is it because of, because I saw that like kind of small motherboard there, is it because of an electrical thing, or is it because of a chemical or a different composition of the battery itself? Mm-hmm. That kind of blew my mind. Like, where's it coming from? Like, because I find it like really amazing. Like, how do you control how the ions go into the battery? I mean, that's mind-boggling.
Yeah, maybe I can comment in 30 seconds, and Billy can take over. So we don't touch or require any changes to the composition, the chemical composition, material composition of the battery. We can work across. So what we are able to do is, with our technology, we are able to probe and find some of the critical parameters of a battery, characteristics of a battery. And our algorithm then can be tuned there. So, it's a combination of hardware and software, right, on how we shape the charging waveform. And then on the hardware side, how is that accepted into the device? So it's a fairly minimal changes, as Billy was talking about, to be able to do that. But that's sort of how, knowing we track 20 parameters, Billy, something like that, 20 to 25 parameters of the battery on the characteristics, and our algorithm tunes for that. And that's how we are able to really make this work. So it's nothing to do with the chemistry. We don't require changes to the battery chemistry at all.
That is amazing. And I have another question, actually.
Sure.
Is that you were mentioning that it's so important for example, mobile phones that have these issues that are really regular issues that they either blow up or burn or, they just die, and there are certain brands that you cannot change their battery. But do they actually want to do that? I mean, do like these brands really are interested in not having this, detrimental action on the batteries as they charge? Because it seems to me like it's like the most easy way for them to kind of take that off your hands and make you buy a new one, basically, right? It's like this programmed obsolescence that it's been, greatly talked about. But maybe batteries are such a mystery, that maybe that's their last bastion. So maybe are they really up for that? What's been your experience so far?
Yeah, so there's a paradigm shift in everyone's thoughts on, electronic devices, and, people are in the media starting to see more and more of what goes into making one of these devices, from mining the rare earth materials and, the amount of production and just overhead in that realm. So I think a lot of consumers are going to be more and more, looking for avenues and different product lines that do say that, hey, this is a more sustainable product because the battery does last longer. You don't have to replace your phone after 2 or 3 years. This may last 4 or 5 now based on the cycle lives that we're achieving in some of these scenarios.
Yeah, and other couple of pieces, I think the whole concept of fast charge, especially for premium or flagship models, that's how they want to differentiate and say you can charge a heck of a lot faster and safer. The other piece of the puzzle, I think, to what Billy was talking about, the whole right to repair regulations in Europe actually are forcing people the cell phone manufacturers and the battery guys people now have to be able to remove the battery and replace it. So in that sense, their whole world is now the battery needs to last as long as electronics do, because if I'm a battery manufacturer, I don't want to give the, let's say, option for a customer to replace my battery with somebody else's battery. So there is that element as well that's playing into what Billy is saying, apart from the whole sustainability ability for corporate goals and so on. I think a technology like this could enable.
That is very interesting. I had another question there. I mean, this is so amazing. I mean, it's a really dark subject. Like, nobody talks about this. So I have a lot of doubts as to not only do the brands want to, I think you touched a really interesting point there, that obviously the battery makers are not going to be happy about changing their own batteries, but do you think we're moving forward towards taking back this idea that products should last longer? Do you think that we're eventually going to go back to that and out of the super disposable thing that we have now? If we go like 40 years back, things were built to last, right? 30, 40, 50, 100 years. Mm-hmm. Now we have a 2-3 year cycle, and that's like, wow, that took long. Do you think this is going to change?
I have my view, but Billy, I don't know if you want to talk, and I'll give my view on this.
Yeah, I mean, I think that is absolutely, and I kind of go back to my prior point a little bit of the consumer is going to start to see this as a feature rather than something that is maybe like a top 3 level feature of saying, hey, this is something that I want to buy a product for because it actually does think about the future. It thinks about minimizing waste. So I think that would be something that would absolutely be compelling to especially the newer generations of consumer.
Yeah, the more sustainable people who think about that, I think it's very valuable. I will say very quickly, sorry, just 30 seconds, let me finish this thought, if you don't mind. So I do believe that the pace of technology change to get new features or capabilities is going to drive the time in which people have to change products or new products come out. But the whole thing with doing something like this is through the life of the product, whether it's 1 year, 3 year, 5 years, your performance does not degrade. Your safety is not degraded, and you're giving the consumer something that's more convenient or more usable in the time frame. So I think there is something to be said for that. Again, the pace of technology change, I think, is what's ultimately going to drive how quickly you have to change products. And we enable the user experience to be consistent throughout that life. So that's one piece. The last piece of the puzzle really quickly is when you talk about big batteries like EVs or grid storage and so on, something like this where you don't degrade the battery goes back to what Billy was talking about in terms of materials and sourcing. You're not damaging the material, so there's a second life. The recycling, you're not recycling damaged batteries or damaged electrolytes, so it's cheaper, easier to dispose, right? So there are advantages from that standpoint. I'm sorry,
Just so you can hear me better. First, I really enjoyed your talk. Thank you so much. And it's not an opportunity I have often to talk to two electrical engineers about what we're really interested in here and why we're here. But there's a larger conversation called smart cities, and we have a table downstairs, and we're talking about that. And I've been working with the state California Energy Commission on a term called demand energy response. And this has to do with like a real time, how are we going to produce the energy in Los Angeles and the state of California now by 2030 to have all these electric vehicles. But it seems like you're kind of super disrupting the conversation, because if you change the way batteries charge and how fast they can charge and how long they can operate, all those calculations that I watched 2 weeks ago from the consultants advising the California Energy Commission on how to do the analysis for the demand energy response for the state, don't seem like they're consistent with your disruptive technology. So I know you guys know what I'm talking about, and I'm not saying it exactly correctly.
Yep.
No,
Because I see you smiling, so it's making sense. But can you talk a little bit to that? Because this is something our team is very, very interested in.
Do you want to take that one?
Sure, I'll take it. I mean, we are also working with some of the consultants. I mean, there are so many different elements that a technology like this can go and touch, right? It's from your analysis in terms of the investment, the capital investments you have to put in place, the life that you take into the calculations and you do. It's about you can go take an EV battery, because normally EV batteries, when it gets to 60% of capacity, you take it out of the EV, okay? But now, because the rate of degradation is so slow, you could take a cheaper battery and then get into the storage world, okay? So that addresses the capital investment world. There is the element of, I think when you talk about city and storage, I don't know that fast charge really matters quite so much as your ability to maintain a capacity. So in other words, if you're trying to put a 6 megawatt sort of a storage facility in place, if your battery keeps degrading over time quickly with existing charging technologies, you got to probably put in an initial capacity of 10 or 15 megawatt hours. With some of these new technologies, you don't need to spend that. So it's not just the fact that you can get a cheaper battery, but also equally that you don't have to have that overhead sitting on top. So we are starting to work through some of those. And I think, as Billy said, we are working with the smaller battery sets today. We are collecting data on the larger batteries. And we are starting to work with some of the consultants who specialize in these analysis and these calculations. And like any new technology, you crawl, you walk, and then you run. So I do fully expect by end of next year and into 26, I think people will be looking at technologies like ours, and there are other technologies where it'll change, I think, the calculations and how you calculate and what you calculate, and I think it'll become more mainstream through next year.
Thank you so much, BC and Billy. We've run out of time. I'd like to personally thank you and congratulate you on this awesome project and company that you're working in. I think it will definitely revolutionize a lot of things that we use on a daily basis. So I'm really thrilled to have you here. Thank you.
That's good, thank you.